No slide. Okay. So today is my last lecture, number 4. And I remind you that next week we're going to have 2 more lectures on Ratner's theory and 4 lectures on Ergodic Ramsey Theory. Okay? So the schedule is on the website if you look there. So today I want to talk a little bit about the relations of these theorems that we discussed in the first 3 lectures, the relations of these theorems with number theory. Okay? So I'm going to give a brief example, not an example, but a condition that guarantees to you that if you prove this condition, then you prove Riemann hypothesis. And this condition is translated in terms of the convergence of equidistribution of horocycle orbits in the modular surface. Okay, so this is the first relation between horocycle flows and number theory. And on the second part of the talk, and which is actually going to be the main part of the talk, I'm going to discuss a little bit about Oppenheim's conjecture. This was a conjecture that was first formulated in 1929, and it was only proved in, I think, in 88 by Margulis. And the way that he proved was using dynamics on homogeneous spaces. Okay? So for that, you're going to have to discuss these 3 things. This specific homogeneous space, and you're going to see why it is so important for applications to number theory. And this is a criterion that tells when a subset of this homogeneous space is going to be pre-compact or relatively compact. And in the end, we are going to see an observation due to Raghunathan that can be, once Raghunathan observed that in order to prove Oppenheim's conjecture, you just need to know properties about the closures of orbits of some flows acting on these kinds of quotient spaces. Okay? So this is going to be the sketch for today. So let's start remembering 2 theorems that we saw yesterday. And the first one is Furstenberg's theorem, which said that if X is a quotient, a homogeneous space that is compact, then the horocycle flow is uniquely ergodic. Right? Everybody remembers this. And the unique measure is Haar measure on that quotient. So in particular, because we have unique ergodicity, the orbits, they equidistribute with respect to the Haar measure. Every x in X is generic for the Haar measure of my quotient. Okay? So this was the case in which you have compactness, and the other case that we spoke about yesterday is the non-compact case. So if X, again a quotient of SL2R by one of its lattices, but now we no longer assume compactness, we assume non-compactness, but we assume finite volume. So if X is not compact, then they classify the invariant ergodic measures for the horocycle flow. So the ergodic and invariant measures for the horocycle flow are either periodic, supported periodic measures supported on periodic orbits, because in this case we know that there are periodic orbits, and the other measure is the Haar measure of the space. Okay? So one thing that I forgot to talk about yesterday is that, of course, if you have a periodic orbit, then this periodic orbit is going to equidistribute with respect to the measure on this orbit. It's nothing but a translation on a circle. What happens in the case that you get an orbit which is not periodic? they also proved that in this case, this point, this initial point, is going to be generic with respect to the Haar measure. So if x in X is not periodic, then it is generic with respect to the Haar measure. Okay? So let's see the special case on which gamma, as usual, is equal to SL to Z. So if gamma is equal to SL to Z, I told to you basically in every talk that the quotient of SL to Z and SL to R and mod SL to Z, it has a fundamental domain, and this fundamental domain can be represented as the unit tangent bundle of this region here. Right? We saw this. So this guy here is the circle that passes through 1 and minus 1. And these two vertical lines is the vertical lines with absolute value equal to 0.5. This is the vertical line 0. So we saw that actually in this example that we have periodic orbits here, right? So every time you get a horizontal segment here, and you consider a vector pointing upwards, if you apply the horocycle flow, it walks like that. Until it reaches this point here. But because of the identifications that you have of this line and this line, this means that you have a closed orbit on the quotient. Okay? So in other words, you could see the fundamental domain, you could see the quotient as something which is like this. And what I drew here is a closed orbit like this for the horocycle flow. Okay? So this phenomenon, it happens until this line doesn't touch this circle. But after it touches a circle, so let's draw the circle in a better way. Okay, that's better. So after it touches the circle, and you begin to walk in the horocycle flow here, when you reach this point, the identifications that you consider no longer make this orbit to be closed. This orbit is no longer going to be closed. Because, because this point is identified with another point. It's Z is sent to minus 1 over Z. So what happens is that you are having an orbit that does something like this. Oops. Okay? So if you get such segment, and this segment is on the height y, let's call this curve the curve that's defined by these vectors on this line to be called gamma y. Okay? So this is an example of a gamma y. Well, it's a finite segment inside the quotient, and you can actually calculate the length of the segment because it's just the length of the segment here on the basis. Because you are in height y and you are in the hyperbolic metric, the length of gamma y is equal to 1 over y. Okay? So you have these paths of orbits inside this quotient. And the question is, what happens when y goes to 0? Because when y goes to 0, the length of these guys begins to grow. And by Dunning-Smiley, one of the consequences of Dunning-Smiley is that these paths, these sizes of orbits, they actually equidistribute with respect to Lebesgue as y goes to 0. Okay? So by Dunning-Smiley, implies that these orbits, they equidistribute with respect to Lebesgue, which in other words means that if you fix any open set U inside this quotient, so here is SL2 Z mod SL2R. So if you fix any such open set inside this quotient, and you count the proportion of the curve that you are considering that falls inside U, and you make this y go to 0, then this should converge to what? To the quotient of to the proportion of U that U occupies in the big set. So it should converge to the measure of U divided by the measure of X. So let us call this X. Okay? So this is what Dani Smiley tells you. And one thing that Don Zagier observed is that if you have a better understanding of how fast this proportion converges to this proportion, so in the sense that if the length of gamma y intersection U divided by the length of gamma y is equal to its limit plus order of y to the 3/4 minus epsilon. So this says that if y goes to 0, this is the rate of the speed of convergence of these proportions to the limit. So if this happens, then the Riemann hypothesis is true. Okay? So this is the first example of the interaction between homogeneous dynamics and number theory. So the Riemann hypothesis can be translated in terms of rate of convergence in the distribution of horocycle orbits in the modular surface. Okay? So, but why is this so? And the reason, the main reason is that this quotient is very special. It can encode a lot of properties, a lot of number theoretical properties. For example, if I'm not mistaken, and Sergio can tell me that, you can characterize the Markovian spectrum in terms of some properties of geodesics inside this quotient here, right? Yeah, so Markovian spectrum is something that tells you about good approximations of irrationals by rationals. And you can get the Markovian spectrum in terms of properties of geodesics in these kinds of quotients, in this quotient in particular, okay? So naturally, the arithmeticity of this guy inside this guy tells you that you can get number theoretical results analyzing flows on this quotient, okay? So this was the first example, and actually in the second example, Oppenheim's conjecture, we are going to see this again, but instead of being SL2R mod SL2Z, we are going to see that what is important to proving Oppenheim's conjecture is SL3R mod SL3Z. So let's first state what Oppenheim's conjecture is. And it's something that tells you about quadratic forms. So first of all, what is a quadratic form? Well, it is a form in some number of variables and to be a form, I mean to be homogeneous. And to be quadratic, I mean to have degree 2. Okay? In other words, it's some polynomial that has this form. Okay? So this is a quadratic form. And what Oppenheim conjecture first in 29, then in final form in 53, was that if Q is a quadratic form in at least 3 variables, and if Q is indefinite, non-degenerate, and non-rational, then when you plug into Q all possible integer vectors, this gives you a dense subset of the real numbers. Okay? So I'm going to explain to you all of these notions that are involved in the conjecture. So I'm going to explain to you what is to be indefinite, non-degenerate, and non-rational. But you could see from now, actually, that is telling you a few things about the coefficients of the quadratic form, right? To say that you have, let's say, arbitrarily small values of Q, when you restrict the domain of Q to integer vectors, you are saying something about arithmetic properties of the coefficients, how the coefficients relate to each other. So this is a number theoretical conjecture, and it was all attempts to prove the conjecture, I mean, since 29 until 88, they were number theoretical, and they were not successful. Some guys proved that it is true for diagonal forms of degree of number of variables at least 5. Another guys proved that it is true for every quadratic form of number of variables at least 21. But no one managed to prove that it is true for 3 variables, which is the most difficult case. Okay? So let's first try to understand what are these notions involved on the statement of the conjecture. So to be indefinite, I think most of you know what it is that it assumes positive and negative values. Okay? Okay? Observe that this is not the same as saying that all the coefficients are either positive or all the coefficients are either negative. We have cases on which the quadratic form is positive definite but has some coefficients which are negative. For example, if you consider Q of xy to be x squared minus 2xy plus y squared, this guy has one negative coefficient, but it is positive definite, right? Because it's x minus y to the square. So it has nothing to do with the coefficients. So this guy, we call it definite. And for example, if I change this minus 2 to minus 3, it is indefinite. Okay? So this is the notion of indefiniteness. The second one I want to say is non-degeneracy. And non-degeneracy means that Q is non-degenerate if, so let's define what is it to be degenerate. So it is going to be degenerate if there exists a change of variables that makes Q become a quadratic form with less variables. If you can give me a change of variables that makes this Q, which initially was supposed to have n variables, to have less than n variables, then we call it degenerate. It's going to be non-degenerate if it's not degenerate, okay? So for example, I'm going to give an example of something which is degenerate. Well, if you just plug into like this. You could call this to be A, you could call this to be B, and then this is going to be a quadratic form in 2 variables only. Okay, so this is the non-degeneracy. And the third one is non-rational. So let's define what is to be rational. And what is to be rational? I mean, you could say, okay, it's to have all the coefficients to be rational. Yes, that's true. But it could also be a multiple of something which has this property. So Q is rational if it is a multiple of some Q0 that belongs to Q of x1 up to xn, okay? And it is non-rational if it's not rational, okay? So these are the notions involved on the conjecture. Question now, why did he conjecture on that way? So why did he require the quadratic form to be indefinite, non-degenerate, and non-rational? And also to have at least 3 variables. Someone can tell me something? Mario? So, you are asking about denseness of something, okay? If this guy is definite, there's no chance to be dense. I mean, it only gets positive values or only gets negative values, no chance to be dense. So good. We understood why it is to be indefinite is important. Why to be non-rational is important. If it is rational, then actually the values that Q is going to attain in integer vectors is going to define a discrete set of R, right? Okay, so non-rational is okay. Why non-degenerate? Well, to understand non-degenerate, we have first to understand why we require to have at least 3 variables. So, note that and the claim is that he asked to have at least 3 variables because the result is not true for 2 variables. So let's give a counterexample of the conjecture that has 2 variables. And the counterexample comes from some Diophantine properties of real numbers. So if you get Q of xy to be equal to x squared minus, and here I'm going to put this guy like this, x squared minus 3 plus 2 square root 2 times y squared, then Q of Z2 is not dense in R. So what is the property about this? The property about this is basically that this guy is the square of an algebraic irrational. Indeed, 3 plus 2 square root 2 is equal to 1 minus square root 2 squared. So call this alpha squared. So in other words, I'm just defining my quadratic form to be of the form x squared minus alpha squared times y squared. And this gives me that Q of xy can be written as x minus alpha y, x plus alpha y. Right? But because of the Diophantine properties of this guy is a badly approximable irrational. So actually there exists C such that for every pair of integers, this holds x over y minus alpha is bigger than C over y squared. Okay? So in other words, this means that for every rational number, for every pair of integers x and y, you have that x minus alpha y is bigger than C over y. So the conclusion is that, for example, if you took x and y to be positive, which actually you can do because if it's not positive, you change x to minus x and the same to y. So if x and y are positive, then Q of xy in absolute value, well, is equal to the absolute value of x minus alpha y, x plus alpha y, right? This value here is at least C over y, and this value here, because x and y, okay, if y is 0, then this is at least 1, so you should check this separate from the other case. I leave this as an exercise. If y is not 0, then this expression is at least alpha y. So this gives you alpha y. So this gives you C alpha. Okay? So this cannot have 0 as an accumulation point. And the conclusion is that Oppenheim's conjecture is not true for this example. So it's not true in general for two variables. Okay, so that is the other assumption on the conjecture. And now we can understand why non-degenerate is also necessary, because you could have a quadratic form which has more than 3 variables, but is degenerate in the sense that when you make the change of coordinates, it gives you, for example, this quadratic form. So if it gives you a quadratic form of less variables, and this quadratic form is equal to this one right here, because the Oppenheim conjecture is not true for this one, it's not going to be true for the other one. So non-degeneracy it's needed because Q could be equal after a change of coordinates it could be equal to, for example, x squared minus 3 plus 2 square root 2 y squared. And because it's not true Oppenheim's conjecture for this one, it could not be true for Q. Okay? So all of these conditions are necessary. And what the conjecture asks is whether these conditions are sufficient. So Margulis proved it in 88, and the way that he proved it was to look at some quotient of Lie groups by lattices. Actually, one specific. So Margulis proved it looking at flows, actually unipotent flows, in the homogeneous space SL3R mod SL3Z. Okay? We already saw that SL2R mod SL2Z is important. It naturally appears in our theoretical applications. And it also appears, SL3R mod SL3Z, it also appears in these kinds of applications. So now we're going to make a break to try to understand a little bit about this quotient space. So now the discussion is about this quotient, which I'm going to call Xn. So Xn I'm going to denote to be SL and R mod Sn and Z. Okay? So first of all, I want to understand what is this space. Well, it has a topology, the induced topology, but there is a nice interpretation about this space. And the interpretation is that it can be seen as the moduli space of unimodular lattices of Rn. So in other words, so Xn is the moduli space of unimodular lattices. And what it is to be unimodular lattices is that the volume of the quotient is equal to 1. So it is unimodular lattices of Rn. Okay? So why is this true? Well, indeed, for each element G in SL and R, we can define a unimodular lattice of Rn. Indeed, for each there is a unimodular lattice of Rn. And the way you define this is just you evaluate G on the canonical basis of Rn, and you have n vectors, and you just consider the lattice which is equal to these n vectors times Z. The sum of integer multiples of these n vectors. Okay? So this guy is a lattice, right? It is a unimodular lattice. Why? Because the basis that generates it has determinant equal to 1. And, okay, so to each guy here, you have associated a unimodular lattice. Why? When two different guys generate the same unimodular lattice of Rn, the condition is that you should be able to send via some change of coordinates with integer coefficients to send the bases GE1, GE2, GEn to the other bases that you have defined by the other element. Let's say HE1, HE2, up to HEn. Because this change of bases has to have integer coordinates, because you are actually multiplied by Z here, this means that you define a matrix which has integer entries that is sending one basis to the other basis. Which in other words means that you are in the situation of G equals to H gamma, where gamma is a matrix of SL and Z. It has determinant equal to 1 because it's sending a basis which has determinant 1 to another basis which has determinant 1. Okay? So the observation is that if G and H belongs to SL and R, they define the same lattice if and only if G equals to H gamma for some gamma in SL and Z. Okay? So this means that the quotient Xn is equal to unimodular lattices. And this shows to you why this quotient is important for number theory. To understand properties of lattices, you are trying to understand properties of numbers. So naturally, if you understand this lattice and its properties of actions of groups and so on, you can translate to number theoretical properties. So for example, if you are in n equal to 2, so x2 is the set of unimodular lattices of R2, right? But you could also see it as the set of flat tori which have unit area. Why? Because every lattice of R2 defines a tori, a torus, a flat torus. If the lattice is unimodular, the torus that it's defining has unit area. So if n is equal to x2, then this can also be seen as the moduli space of unit area flat tori. And for example, this shows to you why x2 is important for geometry. Because it naturally parameterizes all flat tori which have unit area. Okay? This is one of the things that Alex asked me to tell you. He's going to use this next week, this characterization. Okay, so now we know what is this quotient. And actually we know we have an induced topology, the topology that comes from SL and R. Good. Question. Is this quotient compact, non-compact? Does it depend on n? Are there some n's for which this is compact and some others for which it is non-compact? I already told you that if n equals to 2, then it is non-compact, right? And it has finite area. Well, it turns out that this is actually always the case. So Xn is non-compact and has finite volume. Okay? So let's see why it is non-compact. And to see why it is non-compact, I'm just going to introduce a function. So the definition is a function called shortest length vector, and which is defined as the following. You fix an element of xn, so let's call it not gamma but g, okay? And you know that it is a unimodular lattice of Rn. So you look at all the vectors that appear in this lattice. Delete the vector 0 and look at the one who has the smallest length. So define lambda g to be the infimum of the size of V, where V runs over the elements of your lattice which are non-zero. Okay? This is the function called shortest length vector. Okay? And first of all, it is a positive function, right? By definition. The second property of this function is that it is continuous. So claim lambda is continuous. And to understand why it is continuous, we have to consider the topology of the space. This topology of the space is, if you look at a quotient like this, it's very annoying. It's the induced topology. But to have a new interpretation of this guy, right? It is set of lattices. Because it is set of lattices, we have an alternative description of the topology. So here is the description. The topology of Xn can be characterized as follows. And by the topology, I'm going to characterize the topology by convergence. So, a sequence of lattices, GK, converges to another lattice, G, if and only if for each of these GKs you can find a basis, which I'm going to call V1K up to Vnk. There exists a basis of GK and a basis of G called V1 up to Vn. Such that the first vector of the sequence of bases converges to the first vector of this basis, the second to the second, and so on. So if there exists a basis of GK and a basis of G, such that Vik converges to Vi for every I from 1 to n. Okay? So now with this description of the topology, it's very easy to check that this function lambda is continuous. Thus, lambda is continuous. Okay, so now that we know that lambda is continuous, we can check actually that Xn cannot be a compact set. And the reason is very simple, is that there exists a sequence of lattices for which the lambda associated to the sequence goes to 0. So if you had a limit of the sequence of lattices, the lambda of this limit should be 0. But by definition of lambda, this cannot happen. Okay? So, thus, Xn is not compact. And basically because you can define, for example, this lattice here, 1 over k E1 z plus k E2 z, and the rest, you just get the canonical basis. Okay? So this guy is something like, you get something very small in the E1 direction. You get something very big in the E2 direction, and in the other directions you get the usual. Okay? So if you call this GK, then GK has a vector of length 1 over k, and actually is the smallest vector, the length of the smallest vector is 1 over k. So lambda of GK is equal to 1 over k. If GK would converge to something which I'm going to denote by G, thus lambda of G, by the continuity of the function lambda, should be equal to the limit of lambda of GK, which is 0. And this is a contradiction. Okay? So Xn is not compact. Okay. So what the next topic that I wrote there, which is called Mahler's compactness criterion, tells us is that actually the only way to go to infinity on this quotient is that the lambda associated to a sequence should go to 0. So it is a characterization of relatively compact sets. So it is Mahler's compactness criterion. And it tells you when a subset is going to be relatively compact or not. So it says that A contained in Xn is relatively compact And what it is to be relatively compact? To be contained in a compact set. So there is a set which contains A that is compact if and only if the infimum of the values of lambda when you restrict to A is strictly larger than 0. Okay? This is the only way to not having a converging subsequence. So actually because of this is the reason that these kinds of quotients, they are usually depicted as this. And to go here, to converge here, is the same as to have lambda converging to 0. There is only one way to escape to infinity, which is to have lambda converging to 0. And this is the reason that I depicted x2 like this, and people usually depict xn like this. So it's just like it's as if you had 1 over lambda to be a height function. So if 1 over lambda grows, it means that you are up in the quotient. Okay? And if you cut it here, this is going to denote a compact part of your space. So this is usually the description of Xn. And why is this theorem true? One part is very easy, is actually this one. For example, if the limit, the infimum here is 0, then your set cannot be relatively compact. Why? Because you could get a subsequence, you could get a sequence on which the lambdas associated to the sequence are going to 0, and because it's going to 0, you cannot have a convergent subsequence. So one side is easy. The other one, I'm going to leave as an exercise to you, and it's written on the notes. So actually the whole proof I'm going to leave as an exercise. And the idea is that basically you can choose some nice bases of your lattices. It uses a theorem which is called the Minkowski successive minima theorem, which says exactly this, that you can choose some basis which has some nice properties. And once you have this, you have the other part of the theorem. Okay? So now we know more or less the description of our set Xn. And we know that the only way to go to infinity is if lambda goes to 0. Good. So what is the observation of Raghunathan? And the observation of Raghunathan is that he was able to rewrite Oppenheim's conjecture in terms of orbits inside this Xn. So in order to describe Raghunathan's observation, we have to introduce a subgroup. So his observation was the following. Consider a quadratic form and every quadratic form comes with a subgroup which is the, let's say, the subgroup of isometries of this quadratic form. It's called the special orthogonal group. So the definition is that the special orthogonal group of a quadratic form is the set of matrices in SL and R such that Q composed to G is Q. Are the matrices that preserve Q. So Q of Gx is equal to Q of X for every X in Rn. Okay? They are the symmetries of your quadratic form. For example, if Q has 3 variables and it's equal to x squared plus y squared minus z squared, then SO of Q is equal to SO of 2, 1. It's the special orthogonal group of signature 2, 1. Okay? Okay, so what Raghunathan observed is that as being a subgroup of SL and R, SOQ acts on Xn, right? So in the first 3 lectures, we always consider right actions. Here I'm actually considering left action. My Xn was defined as left quotient, and then any subgroup of SL and R acts on this quotient on the left. Okay? So naturally it acts on Xn. So what is Raghunathan's observation? Raghunathan took a particular point here in Xn, which is the canonical lattice, the lattice Zn. So he considered Zn. Okay? And he considered the action of this special orthogonal group on this point Zn. Okay, so this is an orbit. It's all the points of the action of elements here on this lattice. Okay? This is a subset of lattices. This is a subset of Xn. So he observed that if this guy here is not relatively compact, then Oppenheim's conjecture holds for this quadratic form Q. So he gave a precise condition in order to have Oppenheim's conjecture true for Q. And it's in terms of the orbit of the subgroup in a fixed element of Xn. Okay? So you have Xn, and if this orbit here runs away from any compact set, so it goes here to infinity and comes back, and goes even further and comes back. So if this orbit here is like this, then Oppenheim's conjecture is going to be true for this Q. And why is that so? And the way to see this is to see what's the condition that we have. The condition that we have is not relative compactness. And we know by Mahler's compactness criterion when we don't have relative compactness. The only condition is that the only way not to have relatively compactness is that the infimum of lambda associated to the subset is 0, right? So the proof follows Mahler's compactness criterion. By Mahler's compactness criterion, if SOQ Zn is not relatively compact, then there is a sequence in SOQ such that the lattice GK applied to Zn has lambdas converging to 0. Right? This is the conclusion from Mahler's compactness criterion. So to have this lattice with lambda going to 0, it's the same as to have vectors in Zn such that the size of the vector GK applied to VK going to 0, right? The definition of lambda is shortest vector. So there is some VK on which GK, VK goes to 0, right? But if a vector goes to 0, because Q, the quadratic form, is continuous, then Q of this sequence of vectors also goes to 0, right? Correct? But we can get rid of this GK here. Why? Because GK is one of the symmetries of my quadratic form. By the definition of the special orthogonal group, Q of G of anything is equal to Q of this thing. So, actually I could have put here Q of VK, because GK is in a special orthogonal group. This is equal to Q of GK VK. But now GK VK is going to 0, so this goes to 0. Right? So we have a subsequence. We have a sequence of values of Q on integer vectors that converges to 0. And actually is not 0, because we know that this is not 0. Each of these guys is not 0. Okay, so if this happens, we are done. Why? Because Q is, what do you call it? It's homogeneous. So if we multiply Vk by some integer t, this t goes out with t squared. So to say that you have that 0 is an accumulation point of the values of Q in integer vectors implies that actually Q in the integer vectors is dense in R. Okay? So because of this, it follows that Q of Zn is dense in R. Okay? So this proves the observation. So actually, Raghunathan was not the first one to observe this. It was implicit in a paper, I think from the 50s, of Casas and another guy, which now I don't remember the name. But Raghunathan was the first one to spread this relation. I mean, he observed that. He was working on these things of homogeneous flows. So he was trying to get the conjecture using this lemma. And this is exactly what Margulis did. He got this equivalence, and using the equivalence, he proved the conjecture. Okay? So I have half an hour, and I would like to discuss a little bit about Margulis' proof, about the proof of Oppenheim's conjecture, which actually is not going to be Margulis' proof. Why? Because on the sketch that I'm going to give here, we are going to make use of Ratner's theorems. But Ratner's theorems only came after the proof of Margulis. Margulis actually proved a special case of Ratner's theorems for the situation of SL3R mod SL3Z. Okay, so let's go to the proof of Oppenheim's conjecture. And actually, I should tell you that we are going to use a few black boxes in the proof that I'm going to show you here. It's not going to be a complete proof. It's going to use some deep results about algebraic groups. Okay? Okay, so Raghunathan observed that the action of SO key on Zn, on the point Zn, can tell you something about Oppenheim's conjecture. So the first step which I saw before, which I told you before, is that you can assume actually that Q has three variables. That Q is defined only on three variables. Well, the reason of this is that because you can actually check if Oppenheim's conjecture holds for all quadratic forms of some fixed degree, it holds for all quadratic forms of some degree up at least this fixed degree. So if it holds for all degrees, if it holds for every quadratic form of degree 3, then it's going to hold for every quadratic form. Okay? So the assumption is that Q can be chosen to belong to R, X, Y, Z. Okay, so this is the first step. The second step is to try to see what is SOQ, okay? And how do we see this? We see this using the property that Q is indefinite. Because Q is indefinite, it has either signature equal to 2-1 or 1-2. It cannot be equivalent to something which is x squared plus y squared plus z squared. Otherwise, it would be definite. So to say that the signature is either 2-1 or 1-2 is the same as saying that after a change of variables and a dilation, Q becomes the quadratic form x squared plus y squared minus z squared. And then because you have this association between Q and this quadratic form, which I'm going to call Q0, you can get to identify SO of Q in terms of SO of Q0. And actually the property is that these two guys are going to be isomorphic. So because Q0 is this specific one, actually I can put here 2-1, right? SO of the specific guy is SO21. Okay, so we have that SOQ is isomorphic to this. Now we want to apply Ratner's theorems. And in order to apply Ratner's theorems, we should have an action of something which is generated by unipotent elements and also that is connected, right? Well, this guy is not connected. No problem. We can restrict it to the connected component that contains the identity. So the third step is that restrict SOQ to SOQ, connected component of the identity. Okay? This is a connected subgroup. So what remains to check on the conditions of Ratner's theorems is that it is generated by unipotent elements, right? Just like the horocycle flow. So how do we check this? Well, we use that it is isomorphic to SO21. So the fourth step is to observe that SOQ, connected component of identity, is generated by unipotent elements. Okay? And why is that so? Well, I'm going to prove this in 3 steps, 3 parts. The first part is that because SOQ, the connected SOQ is isomorphic to SO21, and actually this isomorphism can be explicit. It is equal to something like this. It is a conjugation. So conjugation fixes the identity, right? Because conjugation fixes the identity, the connected component of the identity of this guy and of this guy are the same. So the first observation is that the connected component of SOQ containing the identity is the same as the connected component of SO21 containing the identity. Okay? And the second condition, the second property, is to try to understand something about the local property of this group. So do you remember how we did, actually we didn't do, but I told you how to be able to analyze local properties of Lie groups? The way to do that is by looking at Lie algebras, right? Lie algebras tell you about local properties of the Lie group. So look at the Lie algebra of SO to 1, which I'm going to denote by small letters, SO to 1. It is an exercise, and it is one of the appendices of the lecture notes, that this Lie algebra is isomorphic to the Lie algebra of the group SL2R. So you have two isomorphic Lie algebras. Once you have two isomorphic Lie algebras, a theorem that I said in the second lecture, which is called the fundamental theorem of Sophus-Lie, tells you that you actually have a local isomorphism between the groups themselves. So SO to 1 and SL to R are locally isomorphic. Okay? But then we are done. Why? If they are locally isomorphic, it means that SO21, the connected component, is generated by unipotent elements. Because we saw yesterday that SL2R is generated by unipotent elements, right? It's generated by the U plus and U minus. So actually I'm going to write the third guy here, is that because SL2R is generated by matrices of the form 1T01 and 10T1, like this. It follows that SO21, more specifically, its connected component containing the identity, is generated by unipotents. Okay? So this is the condition that was missing to be able to prove Ratner's, to apply Ratner's theorems. So now let's apply Ratner's theorems. So we were in the fourth step, so the fifth step is apply Ratner's. It's actually the orbit closure theorem. Okay? So by this theorem, we know that the closure of this orbit is algebraic. So we can write this as L applied in Zn, where L satisfies two properties. The first one is that it should contain, basically is this. It should contain the group that you are acting. Well, up to some conjugation, I'm assuming that this group is this one. Okay? And it should be contained in the whole group. So it's a group intermediate to these two. And the second property that we should have is that LZN is homogeneous. So it's L homogeneous. Okay? So it is nice because only this property here tells you a lot of things about L. And I'm going to use a fact, which is the following. Instead of looking to the groups, look at the Lie algebras of the groups. And the fact is that the Lie algebra of this group here, which is SO21, is a maximal Lie algebra inside the Lie algebra of SL3R. Okay? So maximal in the sense that there is nothing in between them. But there should be something in between, which is L. So either the Lie algebra of L is this or is this. This implies that either the group L is equal to SO21 connected component of the identity, or it is equal to SL3R. Okay? So we are almost there. Why? In case this group L is equal to the whole group, well, of course, the whole group applied to Zn gives you the whole group here. So we're going to have actually that the orbit of SOQ is dense on Xn. So the only part that is remaining in the proof is to discard this property, this possibility here. And here is where we use the black boxes. So by some results on algebraic groups, if you have that L is equal to SO21 connected component, then the conclusion is that the quadratic form that you begin is a rational quadratic form. So this guy is rational. And you assume that it is not rational, right? So this cannot happen. Thus, L is equal to SL3R, which implies that the orbit of Zn under SOQ is dense in the moduli space of uniform lattices. But well, the moduli space of uniform lattices is not compact. So to be dense in a non-compact set means that it is not relatively compact, which is the assumption on Raghunathan's observation, right? So in particular, it is not relatively compact. And then we are done. This concludes the proof of Oppenheim's conjecture. Okay? So note that we proved more. We proved not only that SOQ Zn is relatively compact, but that it is dense, which means that you can get your lattice Zn and apply a symmetry of your quadratic form to send the canonical lattice to any other lattice of your space, right? You could put it in any position that you want. So this is Oppenheim's conjecture. And this is the second application to number theory that I would like to talk about today. And before finishing the lecture, I'm going to talk about something else, which also Alex asked me to talk. So before going to this, do you have any questions?
The lemma is an if and only if.
Yes. Yes. You can check in Alex Eskin's lecture notes that he proves the if and only if. Something else? No. Okay, so in the last 10 minutes, I'm going to talk about the universal elliptic curve. And this is contained in the other appendix of the lecture notes. Why am I going to talk about this? Because this is going to be the quotient space, the homogeneous space on which Alex Eskin is going to try to give a sketch of Ratner's theorems, to prove Ratner's theorems for this homogeneous space, okay? So what is the homogeneous space? Well, you're gonna be afraid of it, but I'm going to explain everything. So it's a quotient of semi-direct products. Okay? Okay, so on this expression we know almost everything that is here, right? We know what SL2R is, R2, SL2Z, Z2, but what is this? So I'm going to talk about semi-direct products. Which is a way to define new groups. So the assumptions are that you have some group N, which I'm going to consider to be an additive group, and another group H, which I'm going to consider to be a multiplicative group, and I'm going to assume that H acts on N. Okay? For example, we know that SL2R acts by linear transformations on R2. And SL2Z acts by the linear transformations also on Z2. So what I want to define here is the same direct product of H and N is the group. And here is the notation H, same direct product N. And this group, well, how can you get a group from two other groups? You could, for example, only consider the products, right? The Cartesian product. So here is going to have actually all the pairs H in H and N in N. Okay? So if you have H and N, you could only consider H times N with the coordinate-wise operations, right? So H1, N1, H2, N2, because I'm assuming H to be multiplicative and N to be additive, I could define this. But here, I would be forgetting this additional property that H acts on N. So I want to see something about the action of H on N. So I'm going to change the operation that I'm going to define on these pairs, and the operation is going to be the following. So is the group this? Topologically, it's just the product of H and N, but the group operation is different. And the group operation is the following. The first coordinate I multiply coordinate-wise, so H1, H2. But now I change. Now I do the following. It's N1 plus the action of H1 on N2. Okay? Because H acts on N, this makes sense. Because it's additive, the group structure of N, this makes sense. Because the group structure of H is multiplicative, this also makes sense. Okay? So, exercise. This is actually a group with this above operation. And it is easy to calculate the inverse of an element. You invert the first coordinate and the second coordinate. You apply the inverse of H to N. So this is the inverse. Proof. So just a proof of this calculation of inverse. Well, let's just calculate the product of this guy and this guy. So hn times h minus 1 minus h minus 1n. H with h minus 1 gives me e. Now, I look here and I see how is the action on the second coordinate. I repeat n, and then I apply h to the second coordinate of the second guy. So plus h of minus h minus 1 n. Right? Well, this minus go outside. H and h minus 1 cancel out. So it gets n minus n. So this is E0, which is the identity on the H semi-direct product with n. Okay, so this is a group. We know actually who is the inverse of this group. And just like the classical product, you could see both H and N inside the same direct product. So note that the first observation is that there is a subgroup of this which is isomorphic to H, and this is just the pairs H0. This is isomorphic to H, and it is a subgroup. So it's a subgroup of the same direct product, isomorphic to H. Okay? Well, to check that it really is a subgroup, just get two guys of this form, multiply them, and conclude that they have the same form. Exercise this. What I want to see is how this subgroup, which I'm also going to denote by H, how does it act on the same direct product? And the claim is that it acts coordinate-wise. Why? Well, let's see. Get an element of the subgroup and apply to something else. H1 and 1. By that formula, I would like you to check that this is actually H, H1, H, and 1. Okay? So it acts on each coordinate. Okay. We have also a copy of N inside the same direct product, which is to look at the pairs En, where N runs over the subgroup. So this guy is a subgroup of the same direct product, okay? And it is isomorphic to N, okay? It is actually a normal, this is not normal. This is normal. It is actually a normal subgroup of this guy here. And the action of this guy on the same direct product acts only on the second coordinate. How to check that? Well, get En, apply to some H1 and 1, and conclude that this should be equal to H1 and 1 plus N. Okay? Okay, so we have the same direct product. We have two subgroups of it, which are H and N. They act on the same direct product. The first one acts on each coordinate. The second only acts on the second coordinate. And now that we know what is a same direct product, we can consider G to be equal to SL to R, same direct product of R2. Because as I said, this guy here, if you look at the linear action of it, it acts on R2 by linear transformations. And we can consider gamma to be SL to Z, same direct product of Z2. Again, because this acts by linear transformations on this. And X is going to be G mod gamma. So I want to conclude the talk today by identifying geometrically who is X. Okay? So how am I going to do this? Well, I'm just going to check when two elements of the big group G are equivalent, are gamma equivalent. And because I'm considering the left action to be equivalent, is the following. So note that two guys, GV and HW, are equivalent in gamma if and only if, let me remember this, so GV gamma is equal to HW gamma, so GV is equal to HW gamma. So, okay, so if and only if the first one multiplied by the inverse of the other belongs to gamma. Okay? This is the definition of left cosets. And okay, so let's make the calculation. So repeat the first one, consider the inverse of the other. So it's H minus 1 minus H minus 1 of W, and this should be gamma. Okay, so what is this multiplication? Well, the first one is GH minus 1. And the second one is V plus V. Just check here. So I made a confusion here. This should be inverse here and this is. Because x equal to y gamma. Yes, so the left coset, so two guys here are equal if and only if x is equal to y gamma. So if and only if y minus 1x is an element of gamma, right? So it should be the inverse here. So the inverse here gives me something which is not this, but which is g minus 1 minus g minus 1 v hw. This should belong to gamma. So let's write this again. And this gives me g minus 1 h. And the second coordinate, you repeat this, minus g minus 1 v. And you act g minus 1 on w. So this gives g minus 1 w. This should belong to gamma. So this is if and only if g minus 1 h. And this can be rewritten as g minus 1 w minus v. This should belong to gamma. So because gamma is SL2Z, same direct product with Z2, this is the same as saying that g minus 1h belong to SL2Z, and g minus 1 of w minus v belongs to Z2. Right? So these are the two equivalences. And this is the same as saying that G SL2Z is equal to H SL2Z. Okay? The left coset is the same. And this is the same as saying that W minus V is this. Okay? So, as we saw, when you get an element of SL2R, you could associate to it a lattice, right? And this lattice is GZ2, right? So the second condition is saying that W minus V belongs to some lattice. And the first condition tells you, if you remember what is the characterization of SL2R mod SL2Z, that is the moduli space of flat tori. So this is telling you that the flat tori that's defined by G and the flat tori that's defined by H are the same, right? So the condition to have two pairs which are the same in the space gamma is that they define the same flat tori and that the subtraction of the 2 points is the same, belongs to the lattice which is defined by the flat tori. In other words, a pair of X is the same as a flat tori with a marked point. So this is the interpretation that Alex is going to use next week. So thus, X is equal to delta V, where delta is a flat unit area, flat torus, and V is a marked point of delta. Okay? So if you remember that the flat tori are parameterized by X2, you should also see X as a fiber bundle over X2. So you have X2 here, and to each point of X2, what do you have? You have a flat torus, delta, and on this flat torus, you are marking the point V. Okay? So X is a fiber bundle over that modular space, the modular surface, whose fibers are flat tori of unit area. So if you could get another guy here, you would have another torus here with marked points. Okay? So this is the description that Alex is going to use next week. The idea is that he's going to prove that the action of the classical horocycle subgroup 1T01, the action of the horocycle subgroup on this homogeneous space is going to satisfy Ratner's properties, Ratner's theorems. So do we have any other question? Okay, so next week we continue with Alex.